So our next unit here is Unit 15. We've only got one other unit beyond this one.
But we're breaking this one up into two.
Hooray! But we're going to break this one up into 2 units.
We only have
Right?
3 tests before finals.
There's right. What we're going to do is we're going to have a quiz/test the Thursday before break. Okay. We will finish up the remaining quiz/test on equilibrium sometime after break, after we discuss equilibrium. And then there is the acids and bases chapter, and we'll have a test on acids and bases.
When did you say the first quiz was?
The first quiz/test is on Thursday of next week.
And what is it?
Reaction. More questions. We're going forward. All right. So reaction rates. Guys, a reaction rate is exactly what it sounds like it is. It is the speed at which a chemical reaction goes. Okay. Technically speaking, the definition is it's a change in concentration of reactants or products per unit of time. Units of time usually are seconds for chemical reactions, although depending on the speed of the reaction, it could be milliseconds or it could be centuries. Some reactions take centuries, like the formation of crystals. Those units, the units of concentration usually are molarity concentrations. So units usually wind up being molarity per second. Okay, so the idea of a chemical reaction happening is governed by something called collision theory. Notice it's our best idea of how reactions happen. Okay. Basically, the idea of collision theory is that molecules are going to react by colliding with each other. That's why it's called collision theory. They have to actually hit each other. And not all collisions are going to wind up making effective reactions. Some collisions between molecules will not be effective. So there's 2 kinds of collisions, the kind that are called effective, the kinds that are called ineffective. So in general, the idea is that the more collisions you've got, the better your chances of having effective collisions are. So the more collisions you've got, the greater your reaction rate tends to be. Right. So in order for a collision to be considered effective, 2 things have to happen. Number 1, the particles have to collide in the right orientation. I like to think about this as like car accidents. Okay. Sometimes cars hit each other head on, right? Okay. Bad stuff happens. Right? Sometimes it's a tailgating situation and the front of one car collides with the back of another car. At other times you're talking about like demolition car derby, like at the county fair, right? And the front of a car slams into the side of a car, right? T-bone. All right. So molecules can collide in similar ways, only they're not governed by only one plane of existence. Molecules have X, Y, and Z coordinates, so they can float into each other and smash into each other from any side and angle. Not all sides and angles are going to be effective. Usually there's only a couple that are effective. All right. We don't need to learn which ones are effective. We just need to have that concept, that idea. We're not going to worry about exact orientations because we can't affect that very well from our perspective. The other thing that's going to affect collisions is whether they're colliding with sufficient energy or not. Okay, that is to say, are they going fast enough when they collide with each other? Because I've seen car accidents where bumps happen. Matter of fact, I was in one last winter. I was backing out of a space at a gas station. I didn't see a guy behind me. He was driving a very, 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 very nice car. I think it was a BMW. And my bumper hit his bumper. I was so freaked out by it. But ultimately, there wasn't enough energy in the collision to do any damage. I got out of the car and I was so apologetic. And the guy just got out. He looked. He looked at me. He looked at his car. He looked at my car. He said, "Are you okay?" I said, "Yeah." He said, "Is everyone else in the car okay?" I said, "Yeah." He said, "That's what bumpers are for." And it was just, I just felt so good about that. But You need to have enough energy for a collision to be effective, basically.
What is?
All right. Things that affect reaction rates. The nice part is we're flying through these notes because you guys already know some of this stuff. Okay. There are 4 basic ideas that are going to affect a reaction rate. Number 1 is surface area. All right. So we could also talk about concentration of reactants. Okay. Temperature at which a reaction occurs. And then finally, the presence of something called a catalyst. I don't think we did a catalyst yesterday, right? So I'm going to have to do a catalyst demo for you guys next week. Okay. Check this out. All right. Factors that affect reaction rates. Surface area. Hey, that's fancy. Surface area. You increase the surface area, you increase the reaction rates. Okay. I think the idea behind that is that A, it makes the orientation easier, and B, it also increases the number of pieces. If you got a solid object like that calcium carbonate that you guys had, you can only get the surface to react. But if you powder it, like we did in lab yesterday, then there's all of the tiny little pieces that can be available for the reaction. Okay. Concentration. More concentration means a higher reaction rate. If you've got more particles, you're going to have more collisions. More collisions means more effective collisions. Okay. Temperature. Okay. Temperature, as it increases the speed at which things collide with each other. That might not necessarily mean that you get a good reaction, but it is going to increase the number of collisions that occur, which again is going to increase the number of effective collisions that are going to occur. So temperature affects the rate of a reaction. And the way that it affects a reaction is that at higher temperatures, greater amount of molecules are going to have greater kinetic energy than the activation energy. So I just want to kind of quickly point out what this graph looks like because this graph is on your homework. All right. So on the y-axis here, you'll see that it says fraction. You'll see that it says fraction of molecules. Basically, what we're talking about here is concentration. You almost could call that molarity. Okay, so it's the number of molecules basically. And over here we've got kinetic energy. Okay, so as we go farther to the right, that's kinetic energy. Okay. This section right here, this line that they've got drawn right there, is what's called the activation energy, or the energy of activation, which is why they abbreviate it EA. And the activation energy is the amount of energy that's needed for a reaction to actually occur. This particular reaction that's in red here is representing a reaction that's at a higher temperature. So notice that the height of the activation energy line is higher. That means that more molecules wind up being able to react in a higher temperature. Notice this blue curve is representing molecules that are generally at a lower temperature. And by I lost the word. I'm trying to talk about the difference between these two lines. Now I'm really stuck because everyone's staring at me. What's the word? By comparison. That's the word. By comparison, the activation energy for the blue line looks to be about half as big. That means that the reaction rate is going to be about half the rate. Does that make sense to you guys?
Why is the blue line like the peak higher than the
The peak is higher because there are more molecules that are at a lower temperature. So the peak is talking about more molecules, right? And the position of the peak is farther to the left, which means that it's a lower temperature. Kinetic energy is directly related to temperature. So this should be a low temp, and this should be higher temp over here. Does that make sense now?
But I would still think that the higher the peak, the more fraction of molecules have more energy.
Okay, so the higher the peak is talking about more molecules, but we have to look at where the peak is to know what kind of energy they have. So when we're looking at where we're looking left to right. So because the peak is here, more of the molecules, the majority of the molecules actually have this, sorry, I can't get this thing to work right,
Slower.
have this amount of energy. In order for the reaction to happen, this amount of energy is necessary right here. So all of these molecules that are over here, this large amount, they don't have enough energy to react. So when they collide, nothing happens. Okay.
Because we're really looking at the part after.
Right. Okay. This shaded area here is describing all of the molecules that have enough energy to possibly react when they collide with each other. There we go. Okay. And we can see that the area of the red part is greater than the area of the blue part. So that means that there's more reaction rates going on.